All right, everyone, let's go for chapter 2 a little bit. See if we can talk about a few things. We've said our share of things already. Let me try to take some selective strikes at this and see what we can say solving some of these problems. It's a lot to say, so let's try to give a decent summary of it without overwhelming anyone regarding the whole process. For example, question number 2 of the practice test of 20. Let me jump around a little bit with this stuff, try to give you some decent content on this without overwhelming us with more information than perhaps is needed when we're doing some of this. Minus W. Well, this is the problem that is there for us. Well, I'll tell you what. This is W, this is 2. W by itself, this is like the last thing you're dealing with anyway, so kind of forget about it. Let it be here, know it's there, and say W. Is W by itself the same as 1 times W? Yeah, it is. It is. So let's see what we got here. Take the negative 3, distribute it, and see what happens. Negative 3W, negative 3 times 2 is negative 6, and this is 1W. Negative 3W plus negative 6 minus 1W plus a negative 1W. We've delivered this speech. Combined like terms. Negative 1W and negative 3W is negative 4W. And negative 6 is negative 6. You can write it like this. Some of the places, like I said, the plus and negative 6 frequently is going to get seen like this. So just be careful how the system, look at how the homework is accepted a lot of times. If you're in the class that's actually doing this stuff for real homework, for real quizzes, for real tests. Those people not in this course, just looking at this for personal edification, a little bit of review, doesn't matter. Either one of these is fine. That works, that works. Plus a negative 6 is the same as minus 6. So you got that right there. There's some interesting algebra here that I think needs to be looked at, so let's do just that. So looking at this, let's look at problem number 3, for example. If you got 3x plus 3 equals 24, the basic premise of algebra, look at like great scholars that have talked about it. I guess I read this in a mathematics poster one time that was published by I don't know who, but it was some sort of mathematical society. They talked about 2 great scholars that had done algebra among certainly very many people who had done mathematics and algebra. But they talk about in the 2nd century, Theophrastus of Alexandria, and in the 8th century, Al-Khwarizmi. So they were big in algebra, and algebra is huge. Algebra is everywhere. You go into calculus, you're still using algebra. Algebra is there, and it's there to stay. It's very useful to solve many problems. The basic premise of algebra is what you do on one side of the equation, you do on the other side of the equation, and it remains an equation. If you add a negative 3 on each side, you always look to get the x all by itself. You try to get the unknown by itself. Well, there's a 3x. I got to get the x by itself. Let me add a negative 3 on each side. I'll add a negative 3 on each side. 3 and negative 3 is 0, so I got the 3x coming right down. 24 and negative 3 is 21. 3 times what number gives me 21? I know it's 7. Tell you what, 1. Divide by the exact same number that's in front of the letter. If that was a negative 3 in front of the letter, divide by a negative 3. If it's a positive 3, divide by a positive 3. 21 divided by 3 is 7. You are done. 4. Gordon bought 4 boxes of chocolates. Each box cost $8.57. How much did he spend? Well, Gordon bought. Each one cost $8.57, and there's 4 of them. Again, you got the calculator, guys. You're allowed to use a calculator. I don't have one on me right now, so let's just go kind of old school, I guess you could say. 4 times 7, 28. 4 times 5 is 20, and 2, 22. 4 times 8, 32, and 2, 34. And there it is. There's a lot to say here, guys. I mean, you could say problem number 5 is a great problem as well. So let's look at it. Problem number 5 is saying solve for V when they're telling you this. And again, we're using a lot of the basic premises of algebra. You do the same thing on each side to solve for it. Well, do you see me do this? You saw me do this right here. And, you know, what do you have to say about it? Well, I got to solve for V. I got to get V by itself. So if I've got 5/9, minus 5/9 is the same as plus a negative 5/9. Tell you what I'm going to do. I'm going to add the opposite. I'm going to add the opposite of 5/9. I'm going to add the opposite of negative 5/9 on each side, which is positive 5/9 on each side. Negative 5/9 and positive 5/9 is out of there. V is going to be negative 2 plus 5/9. Well, that's interesting. How am I going to do this? Well, how did I show you in the very early video how to do this? Don't worry about this. The algebra, make the algebraic arguments now actually solve this. Is negative 2 the same as negative 2 divided by 1? And is this 5/9? I'll tell you what, I got to get these guys to agree. I mean, I got negative 2 over 1 going to have to equal something over 9. I'm going to multiply it by a special one called 9 over 9. 9 times 1 is 9. 9 times negative 2 is negative 18. Negative 18 divided by 9 is negative 2. Okay, that looks pretty good to me. Negative 18 divided by 9, negative 18 divided by 9 is indeed negative 2. Here's 5/9. The rest, add the numerators. Negative 18 and positive 5, negative 18 and positive 5 added together is negative 13. Now, if they want a mixed number there, I'll see how they actually gave the answer. That's the same as 9 goes in here. Negative 1 4/9 or negative 13 over 9. That's how they actually wanted to say it. For number 5, negative 13 over 9 was fine. I guess that'll work. Okay, so let's keep going. They say a lot of stuff. Let's us say a lot of things too, and we'll figure out how we're going to do this whole thing, guys. So keep working on it. If I go a little on the fast side, you guys, obviously this is a film, so you can go back, you can look at it again. I often forget myself, so I don't want to go too slow on this. I sometimes see myself going too slow on this when I look at the films later, especially when you have the opportunity to basically either speed things up, get out of that, or also just stop it and go back and see what's been said. So, see some of the stuff we can say here, guys. If you look at problem number 6, you're looking at 2x equals 2.56. If you divide, there's your original problem. If you divide by 2 on each side, we already talked about this. 2 goes into here 1.28 times. For 7, all this is practice, right? Chapter 2, practice, the Math 107 at MATC, but it's good for anybody, obviously, trying to look at this stuff, how we're going to look at this. 7, they're saying negative 11u minus 8 plus 3u equals 24. You got to solve for u. Well, minus 8 is plus a negative 8. I like to make everything into addition. Just easy long distance stuff. What is negative 11u and positive 3u? It's negative 8u. And this is the negative 8 stays. It's right here. And we got 24. At this point, let's add a positive 8 on each side. Negative 8 and positive 8 is nothing. This and this is 32. We got negative 8u equals 32. You always divide by the exact same number that's in front of the letter. Is that a negative 8? Yeah, you're going to divide by negative 8. They cancel. It's the same as 1. Negative 8 divided by negative 8 is 1. Anything divided by itself is 1. 1 times u is just u. 32 divided by negative 8. Positive divided by negative is a negative answer. 32 divided by 8 is 4. Yeah, but it's a positive divided by a negative, so that's got to be a negative 4. That's all it is, guys. That's all that it is. 8 is saying, so you got this. Again, they want you to solve for y, but there's a lot more gymnastics we have to do here. Let's see how we're going to do it. I'm looking at this. Myself, like I said, anytime I see a minus, I like to go plus a negative. Minus 8 is plus a negative 8. Then I'm going to take this and go here. Then I'm going to go here. 2 times y is 2y. 2 times negative 8 is negative 16. Negative 5y plus 12. All right, let's keep talking. Usually you put the letters over to the left and the numbers over to the right. That's not set in stone anywhere, guys. But the big thing here is it's a good idea. Well, not only a good idea, you have to get the letters all over to one side. All the y's have to be on one side and all the numbers on the other side when you're doing a problem like this. I'll tell you what I'm going to do. Let me get rid of the negative 5y here. I'll add the same thing on each side. How do you eliminate a negative 5y? How about add a positive 5y on each side? Negative 5y and positive 5y is nothing. This and this is, well, 2 bananas and 5 bananas is 7 bananas, not 7 bananas squared. 2 apples and 5 apples is 7 apples. And this is 12. What we have here is 7y plus negative 16. Let's go. Let's add a positive 16 on each side. I'm trying to get the letters on one side. I got them over on one side, and I get the numbers on the other side. Always add something that will eliminate what you want to have eliminated. How do you eliminate a negative 16? You add a positive 16 on each side. Negative 16 and positive 16 is nothing. Divide by the exact same number on each side. You've seen this before. Divide by 7 here. Y is going to be 28 divided by 7. That's 4. And there you go. So on and so forth. Some of these don't lend themselves to a nice, easy, explicit numerical answer. It's done with symbolism that's non-explicitly numeric. In plain English, you got to solve and you got letters for part of the solution. For like problem 9, for example, they've got you. They're saying this. They're saying B equals 10 plus A. They want you to solve for A. They want you to get A by itself. Well, why don't you add a negative 10 on each side? You know, right down the middle here, why don't you add a negative 10 on each side? 10 and negative 10 is nothing. We got A equals B plus a negative 10. A equals B plus a negative 10. Usually they write it in minus notation. Some places they don't. But in those you take and associate with the ALEKS, using ALEKS from McGraw-Hill, they might be going B minus 10 on that. A equals B minus 10. Pretty neat stuff. 10, they say solve for W. It's the same kind of thing going on, guys. I mean, they got for number 10. Number 10. They've got, they want you to solve for W. Solve for W, and they got W over 8 equals G. Well, to undo division, if you want to undo, we wanted here to undo a multiplication to get Y by itself. You undo multiplication by doing division. If you want to undo division, you undo it by multiplying on each side. Let me do that over. I mean, that was kind of a pretty important point here to make on this. So when you're looking at this, if you got W over 8 equals G, if you multiply by 8 on each side, the 8 cancels. And that's number 10. So on and so forth, guys. Let's keep messing with these and see how we can get through it. All right, guys. Let's keep at this, I guess you could say. So they're saying solve for, and that's some interesting stuff, how this plays out, how you're going to do some of this stuff. For number 11, they're giving you a whole bunch of non-numeric, they're giving you a whole bunch of non-explicit numeric symbolism. A whole bunch of non-numeric explicit symbolism. In plain English, we're not really seeing numbers, explicit numbers here. They want you to solve for x. You got to get x all by itself. It's not easy. But I'll tell you what, looking at it, first thing I would do is take this whole thing. This is just, treat that as one chunk of something. Why don't you just divide by k on each side? You got z over k, be careful now, equals x minus h in parentheses. Yeah, you can just easily lose the parentheses at this point because nobody's being added to anybody. This is going to go a lot easier, actually, if you do that. So if you get down to here, that's pretty important. If you want to undo the subtraction, z over k equals x minus h. You want to undo a subtraction, add a positive h on each side and see how it plays out. Or if it's minus h is plus a negative h, how do you undo a negative h? Still add a positive h. It's the same exact mathematics. This stuff cancels out. You end up getting x right here. You get here z over k plus h equals z over k plus h. So, I mean, that's a lot of what's going on here. Let's look at number 12. 12. Number 12. Christine bought N packs of pencils. Each pack has 10 pencils. Write an equation to represent the total number of pencils P that Christine bought. Write an equation to represent the total number of pencils P Christine bought. So P for pencils, she has 10 pencils in every pack and she bought N packs. Usually they put the number out in front. N times 10 or 10 times N. 10 times N is better. Kira is going for a run. Kira is going for a run. She runs for 4 hours at a speed of 6.4 miles per hour. How many miles does she run? An awful lot of miles, that's for sure. I mean, she went a distance X. She was going for 4 hours at 6.4 miles per hour. Four times 4 is 16. 1 right here. 4 times 6, 1. There you go. You don't have to say X. I guess they just write, 25.6 miles. And there you go, guys. Which one was that? Did that? 12, Christine, and then the miles right here. Okay, that's good. All right, so this was for Christine's work, and this is Kira having taken the run. All right, guys, got that? Yeah. And then this is the last answer on the other one. Number 11 there on that one. Well, you solve some inequalities here, I guess, when they're talking about some of this stuff. Got to be careful. There's a number of ways to go with this. For a lot of these, see exactly how they're talking about it. See how we're going to do it. They have different ways they write some of this stuff, guys. We're not going to worry tremendously. Basically, guys, you will solve. There's a couple inequalities, like 3. I think just 3. There's 3 inequalities that I think we need to look at, and we'll look at them and get an idea what the heck's going on here. Number of ways you can look at this. A whole lot of ways you can look at this, I guess you could say. There are 3 inequalities that they talk to us about, you guys. And so let's look at all of them. The thing about these inequalities that you want to always kind of keep in mind here, guys, is that you solve inequalities the exact same way that you solve equations, with the exception. If you yourself introduce multiplication or division by a negative number within the problem, if you introduce it, not that it's there. I mean, if it's already there and it arises while you're solving stuff, it's a different dynamic. They already have negatives in there. That's fine. But if you introduce multiplication or division by a negative number, the direction of the inequality will reverse, will change directions. That's it. That's the big thing to remember when you're doing this. Otherwise, you solve them just like you're solving an algebraic equation. So, there's a lot to be said here, so you got to just be pretty careful when you're doing it. For number 14, for example. For number 14, you got u over 5. You got u over 5 is less than or equal to negative 8. If you want to solve this, you got to get rid of the 5, so you multiply by 5 on each side. So this is what it's looking like. And then you say, okay, I remember what he said. Now look, I want you to be very careful here. Just multiply by 5 on each side. I multiplied by a positive 5 on each side. So the direction of the inequality will remain as it is, just as it is. It does not change. Multiply by 5 on each side. These cancel. You got the u right here. 5 times negative 8 is negative 40. You're done. Done. It's all values of u. And let's see how they went here. They didn't really go incredibly crazy in some of their... There's a lot of ways you can expose what's happening there. They didn't do something that I thought they might have done. Since they didn't do it, I'm not going to do it. Don't worry about that. This is fine as a final answer for what's going on here with this stuff. So you look at this for 14, and you just multiply by 5 on each side, and you're good to go. 15, solve for x. Now you got to be careful again. You got to be careful. Some of these are set up in such a way it's not going to be a big problem. So there's not. We're not going to worry too much. But let's maybe explore this a little bit. We won't have to. The next problem will let us explore it pretty well, actually. Okay, here we go. Here goes nothing. Tell you what. Let me solve this. How am I going to solve it? Well, I got to solve it like it's an equation. I got to get x by itself. Here's a start. Why don't you add a negative 6 on each side? 6 and negative 6 is nothing. 1 and negative 6 is negative 5. So far, so good. I am dividing by 5 to get x by itself. I know there's a negative number here, but it's already in the problem. I'm dividing by 5. I'm introducing division by 5. This won't flip the other way. If I was dividing by negative 5, this inequality, this arrow, would point the other way. That's out of there. Negative 5 divided by positive 5 is negative 1. That's the way to solve it. Usually they put the x, negative 1 is greater than x. That's the same as saying x is less than negative 1. Just make sure that the bigger number is always pointing to the smaller number, whatever order you write them. This didn't flip. The numbers ended up, I just picked it up and, it's like saying Fred is older than John, same as saying that John is younger than Fred. It's the same thing. So the way it comes out like that. Pretty interesting. Number 16 is a great problem to kind of give us an idea of how this stuff flips around quite a bit. And I think we need to look at it. I think it's a good idea to look at it. Well, let's see what we can say, guys. I mean, 16 is a good problem. It's a neat problem. They're saying, again, we got to do what I said. A lot of ways to go. There's a number of ways to play this. There's two ways to play this. Let's play it both ways, actually. If you're looking at this thing, you could say, okay, let's get all the x's over to the left-hand side. Let's get all the numbers over to the right-hand side. So what you have is minus 3x is plus a negative 3x. Okay, we know that. Tell you what I'm going to do. I'm going to add a negative 3x. Tell you what I am going to do. Now, let me try this a couple ways here. Not sure what the best way is to do it. Let me think a little bit. Okay, we said that minus 3x is the same as plus a negative 3x. Okay, sounds good to me. Let me add a positive 3x on each side, so I could cancel out the negative 3x or cancel out the subtraction, however we want to do it. That's 49. This right here, 3x and 3x is 6x. Let me add a negative 7 on each side, or subtract 7 on each side. That's out of there. 49 minus 7 is 42. This is 6x. Fascinating. This, we divide by a positive 6 on each side. Pretend you're solving an equation. Divide by the exact same sign. Divide by the exact same number that's in front of the letter. If it's a negative number, you divide by a negative number. If it's a positive number, you divide by a positive number. That's x. 42 divided by 6 is 7. 7 is greater than or equal to. 7 is greater than or equal to x. 7 is greater than or equal to x. That's the same as saying x is less than or equal to 7. 7, or just read it backwards. 7 is greater than or equal to. 7 is still pointing to x, bigger than x. 7 is greater than or equal to. 7 is greater than or equal to x. A lot of times on the left-hand side, easier to look at it. Okay, that works. Let's look at it another way. And we better be getting the same answer. The whole premise of mathematics, you guys, anybody who's heard me speak about this stuff in person, it's nothing very profound, it's very obvious, but it's still good to say it, I guess. The whole premise of mathematics is to solve problems. If the mathematics is valid and you can do problems in different ways, you better be getting the same exact answers, namely the correct answers. And usually the mathematics is not valid if you're not getting the right answers. So if your mathematics is sound and if you're doing it in different ways, you will get the right answers. That's just the way it is. If you're doing it right, if you're not making any careless errors. Now let's look at this problem again. Let's look at it another way. Let's just get, the big thing here is, guys, let's get to the same conclusion here. You know, let's get to this. You know, it better be that, which is the same as this. I already delivered that speech. So if you got 49 minus 3x is greater, forgive me, wrong thing. 49 minus 3x is greater than or equal to, jumping the gun here, is greater than or equal to 3x plus 7. Let's go. Minus 3x is plus a negative 3x. So what? Good enough. Minus 3x, you know, as we said, right? Minus 3x is plus a negative 3x. Okay, fine. What's your point? Well, my point is I'm going to add a negative 3x on each side. Maybe it makes it easier when you're adding. Adding stuff is always easier, I think. 3x and negative 3x is nothing. Here's 7 for you. Negative 3x and negative 3x is negative 6x. And this is 49. So, okay. Let's try to get the x's by themselves. Well, they already kind of are. It's already here. It's on the left side. I want it to be on the left side. Let me add a negative 49 on each side. Here's that tug of war again. We've already got the introduction stuff. How are you going to do the tug of wars? Well, 49 and a negative 49 added together is 0. You got negative 6x right here. And you got 7 and negative 49 is negative 42. This is interesting. I got to get to that conclusion circled in green. Let's have a look here. You got negative 6x is greater than or equal to negative 42. Yeah, I agree. I'm going to solve for x. I'm going to stop right there. I'm going to solve for x. To solve for x, I got to get negative 6x to not be negative 6x anymore. The coefficient negative 6x has to disappear. I will introduce division by a negative number, the same negative number on each side. If you introduce multiplication or division by a negative number, the direction of your inequality will change. If you introduce multiplication or division by a negative number, the direction of your inequality will reverse. I just reversed it. It was going this way. You just saw me erase it, and I put it that way. Negative 6 is 1. Negative divided by negative is positive. Negative 42 divided by negative 6 is the same as 42 divided by 6. Guys, that's the same answer I have over there in green. These are the same. Same answers I got over there, I got over here. Pretty important stuff, pretty neat stuff. For 17, 18, 19, and 20, well, let's go. I mean, 17's got something interesting as well. It's got a little bit of an inequality here. For 17, they're saying write inequalities to represent the situations below. They got two different situations. I'm assuming, let me kind of look at it here. Write inequalities to represent the situations below. To qualify for the championship, a runner must complete the race in less than 55 minutes. Use T to represent the time in minutes of a runner who qualifies for the championship. Careful here. To qualify for the championship, a runner must complete the race in less than 55 minutes. Not less than or equal to, less than, strictly speaking. T has got to be less than 55, not less than or equal to. Period. End of the story. That's how that one goes. For the first part of 17. The other one's saying to be eligible for financial aid, a student must earn no more than $15,000 per year. Use S to represent the yearly earnings in dollars of a student eligible for financial aid. So, S, no more than 15,000. It could hit 15,000 as a max. Can't be more than that, though. Can't be more than that. So that's of interest as well. So there's the S that they were talking about on that. That was 17. They say some stuff. I want to give myself a little bit of room on this. Let's proceed a little bit for 18, 19, and 20. Okay. For 18, now they got different ways to do this stuff. They got this thing called the substitution method. Other times they don't really, I don't know, they specify different things. I don't know that it's, there's a number of things that can be said, I guess. I think it needs to be said. I'll try to not water it down, but maybe make it a little more reasonable to look at, actually. For problem number 18, they're giving a problem called, these are two equations in two unknowns. The unknowns are x and y. This first equation has two unknowns. This second equation associated with the first equation, but a different equation, independent from the first equation, they're independent of one another, is 3x plus 5y equals negative 13. The big thing here, you guys, the big thing here is there are two equations and two unknowns. You always need as many equations. You always need as many equations as you have unknowns. Independent equations. They can't be the same equation kind of disguised to look differently. By, oh, hey man, I just divided each side of the equation by 10 and it looks a lot different than the first equation. Or I multiplied each side of the equation by negative 50 and they sure look a little different at first glance. Those aren't independent equations. They're basically the same equations. And those are two equations that are really one equation, and you can't do anything with it to get an independent solution. You need as many equations as you have unknowns. To solve equations like this, they can be any number of them. There's some beautiful mathematics known as Cramer's rule, where you can use determinants to solve as many equations in as many unknowns as you wish. As long as the number of unknowns is equal to the number of equations, and all the equations are independent of one another, you could have 1 billion equations in 1 billion unknowns, and if the billion equations are independent equations of one another, independent linear equations, all 1 billion of them are independent linear equations from one another, those billion equations in 1 billion unknowns could be solved using determinants, using Cramer's rule. Some pretty fascinating stuff when they talk about this. We're not really going there. There's other ways things can be solved theoretically as well, take longer. Cramer's rule is probably more efficient, especially lends itself maybe to a computer program if the numbers are really big. So it's probably really good that way. Looking at this, they want you to use substitution. So you want you to take one of these equations and solve for one of the variables, and then plug that variable, that solved in variable, plug in, substitute the value for that solved variable, put it in the second equation, let's say. I'll look at the first equation. If I looked at x minus 3y equals 19, and I were to add a positive 3y on each side, you know, the minus 3y is plus a negative 3y, or leave it like that. Minus 3y plus 3y goes to 0. X is equal to 3y plus 19. I guess if I know what y is, plug it in here, it'll tell me what x is. Well, I'll tell you what, if x is equal to this, if x is equal to this right here, wherever you see an x over here, wherever you see an x over here, plug in 3y plus 19. What does that accomplish? X is 3y plus 19. What does that accomplish? You end up getting one equation and one unknown, and that's stuff we've been doing already. So if you look at it, the x is the same as that. Let's go. Let's see what happens. 3 times 3y is 9y. 3 times 19 is 57. Here's 9y, here's 5y. Let's get them together. 9y and 5y is 14y. 57 is 57. Negative 13 is negative 13. You got 14y plus 57 equals negative 13. Kind of running out of chalk again here. Let me, a little bit here. So let me, let's go. Let's add a negative 57 on each side. 57 and negative 57 is 0. You always add what's going to get rid of what you want gotten rid of. You almost got the y by itself. You got a 14y here. What's a loss of 13 and another loss of 57? It's a loss, a bigger loss. What's negative 13 and negative 57? Negative 70. 14y equals negative 70. Negative 70 divided by 14, negative 5. Yeah, but we're not done. Y is negative 5. Put a negative 5 right here. That's the good thing about it with the substitution method. Plug it in there and see what happens. What's x going to be? It's going to be 3 times negative 5 plus 19. Times negative 5, not plus negative 5. It's going to be 3 times negative 5 plus 19. 3 times negative 5 is negative 15. Negative 15 and a positive 19 Negative 15 and positive 19 is 4. X equals 4. Y equals negative 5. And that's it. You've now solved 2 equations and 2 unknowns. Solve the following system. Well, this one's, you can do something called the elimination method for this other one. It's maybe a little more efficient to do. Let me get one more piece of chalk here, guys, and figure out what's going on here. So for 19, how are we going to do this? I mean, let's start this thing off a little bit, I guess you could say. I'll end up erasing this eventually, but let's start with 19 a little bit and see what we can say. You can do this thing called the elimination method for that one. For 19, if you got 2 independent equations and 2 unknowns, two independent equations and 2 of the same unknowns, x and y, 3x plus 4y equals 8, and 6x plus 4y equals 20. Well, I'll tell you what I'm going to do, guys. I'm looking at this. There's probably a number of ways you could do this. To me, the easiest thing that jumps in mind is if this equals that and this equals that, if all of this equals all of that and this equals that, then all of this plus this equals all of that plus that. True. Tell you what I'm going to do. What do you say I take this guy right here and try to get a negative 4y and then add it on to this positive 4y and see what happens? This is maybe easier done than said, so let's do it. If you multiply each side of the equation by negative 1, if you multiply each side of the equation by negative 1, some interesting things happen. Negative 1 times 3x is negative 3x. Negative 1 times positive 4y is negative 4y. That's significant. And negative 1 times 8 is negative 8. Well, I manipulated the first equation to get this. It's actually identical to the first equation, just means you multiplied by negative 1 on each side to get this. The first equation has been altered, but it's still essentially the same equation. It's got a different look to it. I multiplied by negative 1 on each side for the first equation. Now I got these 2 equations. This is really the first equation, just a different look. If 2 things are equal to each other, and they are, well, if all this equals all that, and this equals that, then all this plus this will be the same as all that plus that. Add the 2 equations together. Negative 3x plus 6x is 3x. Negative 3x plus 6x is 3x. Negative 4y plus 4y is 0. That's out of there. It's not there. Negative 8 and positive 20 is 12. 3x equals 12. 3 times 4 is 12. I'm going to pretend I don't know that. We do know, indeed, that 3 times 4 is 12. 4 is the answer. Divide by 3, positive 3. X equals 12 divided by 3. 12 divided by 3 is 4. Absolutely it is. Now we find y, and we're in good shape. Well, to find y, you can go into the original 2 equations and solve for y. I'll tell you what. Let me take 6x plus 4y equals 20. Let me take 6x plus 4y that one. And let me just plug in some stuff and see what happens. 6x, just this one right here, 6x plus 4y equals 20 is equal to 4. So let me put 6 times 4 plus 4y. I don't know what 4y is. I got 20. 6 times 4 is 24. 4y is 4y. And this is 20. Interesting. So we got, let's see here, guys. Kind of running out of room here, but not too bad. Let's write this a little more room for ourselves. We got 24 plus 4y equals 20. Let me add a negative 24 on each side, or subtract 24 on each side. (4y) equal, well, let's see here, that goes. 20 24 is negative 4. Divide by 4 on each side. Y equals negative 4 divided by 4. Y equals negative 4 divided by 4. That's negative 1. And there it is. And there it is. Again, just follow the argument. Once you get one of the letters, once you know what the numeric value, once you know what the explicit numeric value is of one of the letters, you plug in that numeric value into the other equation, into either equation, plug in what you know into either one of the original equations, and then solve for the unknown, the way you know how to do it algebraically, and you'll be fine. 20 asks a certain question here. I mean, we could almost not do it, but maybe we need to do it. So let's look at it. Let's have a look really carefully here. Yeah. Two systems of equations are given below. For each system, choose the best description of its solution. If applicable, give the solution. This stuff might be a little more easier said than done. It might be more easier done than said. So that's a good thing if you're looking to solve some of these problems, guys. And again, the stuff is going to scroll. All of these practice exams are going to scroll at the end of the video. All these practice exams, the solution they are, and their numeric solution and their solutions, they're going to scroll at the end of each of the videos for each particular practice exam that we're talking about. So let's look. So for 20, I mean, there's a lot that can get said here, I guess. This is interesting. For number, okay. Forgive me, guys. It's great to use sometimes, but to write down stuff with a thin line is not always the best. All right, so let's go 20 right here. Here's number 20. They're saying for system A, this is system A, and they're just saying, okay, tell me what you think about system A. I think when you acquire enough experience about this, you'll look at something like this, and you'll see something. Well, I'll tell you what you're going to see in a second here. You see this right here? This is a very interesting point. If you were to take these two equations and add them, you get something very interesting. 2x and negative 2x is 0. Negative y and y is 0. Negative 9 and 9 is 0. You end up getting something that's trivial called 0 equals 0. If you ever get 5 equals 5, or 10 equals 10, or 0 equals 0, or negative 51 equals negative 51, that's an identity. There's going to be an infinite number of solutions here. This system has infinitely many solutions that work. You know, the solution set is the set of all x such that it's the set of all x and y. It's the set of all, we're not going to make a big deal out of this, guys, because we usually don't emphasize it greatly, but it's the set of all x and y. It's the set of all x and y such that 2x minus y equals negative 9. It's that set. Anything on that line, any ordered pair that lies on the equation of this line in two-dimensional space, for our purposes, any values of x and y that satisfy this equation, they are actually the points on a straight line if you graph them in two-dimensional space. There's an infinite number of those points. There's an infinite number of solutions. It's that simple. You can't really solve this. And the reason there's an infinite number of solutions is, in this case, these are not independent equations. They are the same equation. If they're the same equation, you can't get down to something more specific. You cannot get to a unique solution. You can't say there's no solution, though, because there's an infinite number of solutions. So, and this all implies number of solutions according to this, and they satisfy this. How do you know that's true? If you were to take and multiply by negative 1 on each side of this equation, minus y is minus 1y. Minus 1y is plus a negative 1y. Plus 1 is 1y. Negative 1 times 2x is negative 2x. Negative 1 times negative 1 is positive 1. The y stays, that's positive 1y. Negative 1 times negative 9 is 9. Well, I just said it. If you multiply these two, if you multiply by negative 1 on this side, negative 1 times negative 9 is positive 9. Multiply by negative 1 on this side, you get negative 2x, you get 1y here. You end up getting the same equation, which means identical equations just written in a different manner. There's an infinite number of solutions in these circumstances, satisfying the equation of this line. You can't get a unique solution. Who knows? Maybe the other one gets us in a better spot. B is saying, okay, so for B, we're saying, they're saying, now this one we might be able to do this with the addition method, the elimination method they call it, or they call it the addition method or elimination method, depending where you go, where you look, what books you're looking at. This one, I think we're out of the woods, you guys. There should be one unique solution here. You can't say sometimes there's no solution. If you ever did some stuff and you ended up getting 0 equals 5 or something, there's no solution there. Not an infinite number of solutions, not even a unique solution. There's no solution there. Those are indicative of parallel lines. There has to be an intersection in two-dimensional space for there to be a solution or solutions. If there's one intersection, it's a unique solution. If they're right on top of each other, there's an infinite number of solutions because the intersection is an infinite number of points. If they are parallel lines, they never intersect, and then there's no solutions. Well, in this particular case, you guys, x is the same as 1x, negative x is the same as negative 1x. Tell you what I'm going to do. Let me just add these two, because things are going to cancel left and right here. And negative 1x is 0. 4y and positive 4y is 8y. 7 and 1 is 8. Wait a minute, that's a pretty easy way out of this thing. 8y equals 8. Divide by 8 on each side. Y equals 1. Sounds good to me. If y equals 1, I can go back to either one of the original equations. Let's use that one. It doesn't have any negatives in there. We got 1x plus 4y equals 7. 1x plus 4y equals 7. Y equals 1. Well, let's see where this is going to go. 1 times x. 1 times x is just 1x. 4 times 1 is 4. 7 is 7. Let me subtract 4 on each side, or add a negative 4 on each side. 1x is 7. 1 times what number will give me 7? It's 7. Divide by 1 on each side. Divide by 1 on each side. 7 divided by 1 is 7. At the end of the day, guys, yeah, there is a unique solution. X equals 7. 1. And there you go. And there we have it. Well, I mean, I'm not always going to be going through the practice exam questions, but I think this one had enough really strong examples. I thought it was important to maybe do just that on this one, guys. All right. So that was test number 2, a test on chapter 2 pertaining to this. I appreciate your time. There'll be more to come.